Ha sido un completo placer, no solo a nivel profesional. El trabajo que está haciendo el profesor es impresionante, ya lo verán ustedes, pero analiza el tema de energía solar no solo desde el punto de vista científico, sino con una visión completamente sistémica de qué es lo que requiere la energía solar para incrementar su penetración en los mercados eléctricos a nivel mundial. Desde el punto de vista social, económico, científico, tecnológico, una visión que realmente es impresionante. Pero también, y a título personal, pues ha sido un placer trabajar con el profesor, que realmente hemos encontrado una persona muy amable, muy humilde, brillante. Un placer, de nuevo. Sin más preámbulo, les dejo con el profesor Tonio Buonassisi y muchas gracias.
Okay. Gracias por la introducción. Yo he crecido en Brasil, entonces hablo una especie de portuñol, pero en esta presentación no te haré sufrir. Hablaré en inglés porque es mejor. We'll speak in English about the technological innovation opportunities in photovoltaics, R&D, manufacturing, and adoption in a global environment. Increasingly, photovoltaics is becoming democratized. In the past, it was within the realm of niche technology in the United States, in Germany, Japan, and increasingly it's being manufactured and installed worldwide. I'm going to describe a few of the transformational changes that have come about during the last 35 years that have resulted in this, and I'm going to hopefully excite you a little bit about the science behind it. Now, I know many of you probably have children, and the children come to you and ask all sorts of fun questions, like, why is the sky blue, right? It makes you wonder. How does a solar cell work? Maybe by the end of this talk, you'll be able to explain to them not only how a solar cell works, but also connect the dots between some of the basic research that's being done, the applied research that's being done together with companies and within companies, and these greater themes like market penetration of solar, grid adoption, and so forth. So I have to acknowledge my team of researchers at MIT. This is the team right here. You probably recognize Sergio. He's been here over the summertime. He is Mexican. He born and raised in Mexico, but he's a member of our research group. And you can see him at a recent photovoltaics conference here holding an award for Best Poster Prize. So he's not only a superstar here in the ministry, but also back home in the laboratory. So we'll go to the next slide. I wanted to start with some context of what has changed during the last 15 years or so, 20 years. What has emerged? What has changed during the last 15 years that make photovoltaics an interesting technology today rather than a niche technology? On the y-axis of this plot, we have module price. This is the price for per watt of a PV module. The dollar sign is US dollars. All throughout the presentation will be US dollars. Per watt. So typically a module that's about this big, a photovoltaic module, is somewhere in the high 200s, low 300s of watts. So you can multiply these numbers by 200, 300 to get a sense of the price of a module. There may be, on a typical rooftop, something like 12 modules or more. So you get a sense of the total price of the module component of the system. What's shown is a dramatic price reduction. There have been some hiccups in the market, but overall, pretty dramatic price reduction of the module in recent years. This has emerged. This makes photovoltaics really interesting, not only from a residential, utility scale, grid adoption competing directly against fossil fuels, but also in terms of integrating photovoltaics with other technologies. Right? So you're hearing more about photovoltaics be integrated into bus station roofs, in lighting, maybe even on car rooftops. It's because of this emergence right here. The driving force for that emergence is what's shown on in the black and on the right-hand side of the y-axis, module production. This is global production of photovoltaic modules, and you can see an exponential rise of solar photovoltaic module production. If we move to the next slide, you'll see it broken down by region. This is the production or manufacturing by region. I'd like to draw your attention to the purple in this chart. That is China and Taiwan, mostly China. If we go back a decade, 2004, you'll notice that the purple is around 5%. If we go to recent years, the purple is accounting for about 60% of all global production. This is a result of an intentional industrial policy in China to encourage manufacturing of photovoltaic modules, sensing a market opportunity, sensing an opportunity perhaps for a higher margin, high technology product, investing in the manufacturing so as to gain market share. right? And to be able to employ large numbers of Chinese graduates from technological institutes and engineers into this growing field. Next slide. I'm showing here a system perspective. So I talked about the photovoltaic module. Now I'm talking about the system itself, and in particular the installed system residential United States. So on houses, rooftops, just like my house in Cambridge, Massachusetts. This is, on the y-axis, the share of installed US system price for residential, and it's comparing the blue, which is the module, and the red, which is everything else, the power electronics, the installation, the labor, the permitting, the customer acquisition costs, everything else is in the red. And this is the share of US residential system price. Note that in Germany, utility, it's about 50-50, everything else in the module. In US residential, this wide gap has grown, about 80-20 in recent years, because of the module oversupply. The Chinese were too successful at manufacturing modules. Right? So the central government encouraged the provincial governments to invest in manufacturing. They all did. Too many solar photovoltaic modules hit the market. The price went down, and you had an oversupply of the module. The price component of the module went down, and the relative fraction of the installed system price of everything else went up. And this is an anomaly of the US residential market. Again, in German utility, and in US utility and commercial, it's closer to 50-50. But this brings up an interesting observation. In the mid-2000s, there was a shortage of manufactured PV modules. In the late 2000s, there was an oversupply of the modules. And you can see how the profit margin was shifting back and forth between these two different segments, the module manufacturers and the installers. And this is a very interesting dynamic, one that colors investment of where you would build a factory, of what segment of the value chain you would invest in. And of course, for R&D, there are a lot of pressures, short-term pressures. When the module shortage is occurring, you're exploring every other alternative to make a module, any material available to humankind. And during module oversupply conditions, when profit margins are very, very low or even negative, there's a pressure to streamline costs and to squeeze out the costs. So we'll be talking about this dynamic and explaining why it happens, and in explaining how we can look beyond the short-term market fluctuations and develop a long-term R&D strategy to advance the field. Next slide. Next. Okay, so here is why R&D is needed on the module side. We are about, in the United States, about a factor of 2 when we consider the minimum sustainable price for PV modules. We're about a factor of 2 away from being widely competitive with traditional sources of electricity without subsidies. And in Mexico, we're probably a little bit closer than a factor of 2 because of the higher electricity rates. This is showing you the price. The very first curve I showed you was price versus time. This is, again, price versus time, starting in March 2007 and ending in September 2013. So over the last 7 years. And I'm going to break it down in terms of the polysilicon. This is the input feedstock material to make the wafers, to make the cells, to make the modules. So this is the feedstock material to make the solar modules. The margin of the companies up here, this is what the companies will reinvest for their next factory. This is what the shareholders of the companies will be able to extract value upon, dividends. And then everything else is in gray here. And you'll notice that when there was a period of oversupply in the mid-2000s, very large margins for solar photovoltaic manufacturers. The market was sending a signal to investors to invest in photovoltaic manufacturing. Make modules. Your margins will be very high. When the oversupply condition hit, because there were too many modules being made, the margins were compressed to the point where the operating margins were negative for a large portion of this period right here for many companies. There were still a few that were making slightly positive operating margins. And the polysilicon, the feedstock prices got squeezed as well. And the reason this plot is concerning is because everything else, which is really the core of the module, it's the material that makes up the module, like the glass, the aluminum frame, the encapsulants, the processing equipment used to make the module. Everything else did not decrease exceptionally much, meaning there was technological innovation, there was learning, but not nearly enough to make a sustainable price reduction. So if we enter an undersupply condition again, where the demand is exceeding supply, we can see a rebound in the margins, maybe even the feedstock material goes up, and the prices might not stay low. We already see this effect slightly in the United States, is compounded with the import tariff, but we see a rise of about 10% within the last year of Chinese module prices. So to make a sustainable reduction in price, R&D is needed, research and development is needed, technological innovation is needed. Slide. So why do we experience these periods of oversupply and undersupply? Why do we exist in this oscillation between high margins, low margins in this industry? This is symptomatic of the semiconductor industry, period. Anything that uses highly purified silicon as its feedstock material. Now, silicon is the second most abundant element on the Earth's crust. You walk outside, you pick up some clay from the ground, you have trillions of atoms of silicon in your hand. It's not lacking on the planet. But to make a solar cell, we need to strip the oxygen atoms away from the silicon, reduce and refine it to its purified state. And to do that, we gasify the silicon and distill it, much like we distill alcohol. And this is a distillation plant, a refinery, a silane refinery. These things cost a few $1 billion to put up, and because of the large capital investment, can take anywhere between 18 to 24 months to build. And of course, if you factor in as well the time spent convincing the board of the company to put down that size of capital, and then convincing the investors to put in the money, it can be much more than that. And so the long lead time of the input material results in these oscillations of oversupply and undersupply. Any business sector that has this similar effect, right, will see periods of oversupply and undersupply. A great example in agriculture is hog farming, pigs, right? So it takes a few tens of months to raise pigs to the point where you can market them. And so the market sends a signal to everybody here, imagine you're all farmers, and market sends a signal to you saying, raise new pigs, the price is high, pork is high. So you start raising pigs, and by the time you bring them to market, everyone else has done the same thing, the price of pigs collapses. Right? So this is the oscillatory business environment that is so to the semiconductor industry, making computer chips for your phones or for your laptops. Next slide, please. Yeah, showing the rebounding of the polysilicon price over the last year, going from $18 a kilo to $21 a kilo blended, the global spot market price going up from 17 to 20%. So you can see some stiffening of prices already, indicating that we might be trending back toward a period of undersupply. So the context is the following. Module prices today are only 1.5% of what they were 35 years ago. So 35 years ago, modules were about 100 times more expensive than they are today. That is what has emerged. The cumulative effect of a lot of R&D, a lot of investment, Germany's demand pull program for subsidizing installations, China's subsidy program for subsidizing manufacturing. The cumulative effect of all of this is that PV module prices today are about 1.5% of their value 35 years ago. They're still about 2x too expensive, and here I'm not calculating necessarily market price, in which case you might have negative margins. I'm calculating a minimum sustainable price, which is a cost plus the minimum margin necessary to survive as a company. When your weighted average cost of capital, your WACC, equals the rate of return that the investors are expecting. So it's about 2x too expensive to ensure widespread grid adoption. So innovation is needed to sustainably drive down the cost and the price of PV. That gray section, the everything else. Input material prices are, right now, are pretty much fully compressed as are margins, and we might see some stiffening of prices coming in the future. Silicon PV module pricing is cyclical, and to make an impact, a long-term strategy is recommended. This is very, very important. If you just look at the market conditions within the last year or two, it's just a small snapshot in time. What's helpful is to take a longer perspective and develop cost models that will predict where the industry will go. Right. And a roadmap is very helpful in this regard. Impacts can be had over the entire value chain, and I'll get to this toward the very end of the talk. And increasingly, a system perspective is necessary. So how do we design or think about an R&D strategy for our laboratory? I'm a researcher. I spend most of my time thinking about technical stuff. Things like quantum mechanics or the effect of some strange defect, iron impurities on solar cell performance. But when I go to a funding agency and have to explain myself, why are you investing in our laboratory? We're a university, so first and foremost, we educate people and we contribute to the workforce. In terms of the research impact, we have to define the research impact in the context of where the market is going, be able to show that the technologies we're developing have on-ramps into industry, have a connection, and that they're going to make, or they have a chance of making an impact. It's higher risk research, but some fraction, hopefully much more than 10 or 20% of our research should have an industrial impact, and we should be able to point to what they are. So we develop an R&D strategy in the context of a rapidly evolving market. This is the price versus time. The overall trend is bending toward low prices, but we have these oscillations. And in periods of oversupply, undersupply, oversupply, undersupply, and so forth, we are suffering different pressures. So in an oversupply condition, when prices are going down very fast, the pressures of the market are to focus on the most mature technologies, to improve the efficiency, and drop R&D on other technologies. This is a short-term view, the short-sighted view. In periods of undersupply, prices go up. People panic, no feedstock materials are available. People are exploring every alternative technology. They forget about cost, efficiency, reliability. All they care about is getting the modules to put out in the field, right? Because they have a contract that's inked with a customer. They need to supply those modules by a certain date, and they get desperate. So the industry shifts occur rather frequently. And I'm going to exemplify this by the International Technology Roadmap for PV. This is a group of companies that get together, I think in Germany every year, and decide what the long-term R&D perspective should be. And this is just to demonstrate how often these roadmapping exercises go wrong if you're just looking in the near term. So back in 2011, when they produced the roadmap, there was a new hot material, 2011, right here, new hot material called mono-like silicon. And it was all the rage in R&D. And so everybody in industry thought that this thing was going to go up to be a dominant material by 2020. So next slide. You can see the little arrow right here. Keep in mind about 50%. By the 2012 roadmap, that number had already dropped to about 10% of the market when people realized that there were some production issues. We had looked at the material in 2010, saw that it had a severe problem with a certain type of defect called dislocations, what Sergio spends most of his time thinking about back at MIT. And we had discounted the material as likely not to succeed. And sure enough, over the subsequent years, industry realized this and began to discount it. In 2013, it wasn't even on the roadmap anymore. So it's important not only to look at the near-term trends, but to develop your own sense of intuition about where the technology is heading. And one way to do that is through a cost model. So our perspective, our long-term perspective, is driven by a cost model. Next slide. This is an example, a few snapshots of an Excel spreadsheet that you can download from the internet. The address is right down here on the lower left-hand side, the http://pv.mit.edu/TMA, Technical Market Assessment. You can download this on the web, play with it, change the input numbers, and see what happens. Using input numbers that are over hundreds of cells, and I mean hundreds of cells, and hundreds of cells, we can, with really good technical granularity, begin influencing different parameters. These are all industry validated, so we ship them out to several industrial partners. They've confirmed, sometimes tugged at the numbers a bit, and we can figure out where we're at, where industry is going, what additional innovations need to happen for us to really drive the technology forward, to drive the cost down by that famous factor of 2. And the key messages are that in the medium term, innovation areas, we need to increase the efficiency of the panels by about 25% relative, reduce the capital expenses by 10 is minimum, 100 has some additional benefits I'll describe later. So CapEx is your initial capital investment for the factory. So your capital expenditures, that's the equipment that makes the solar cells, that's the factory shell that includes the roof, the HVAC system, the water, the waste supply, and so forth. So these are fixed costs that you have to pay forward in time when you borrow the money. And so they affect you twice, not only as depreciation expenses in your cost structure, but also they affect the weighted average cost of capital, so that increases your minimum sustainable price. And lastly, improving materials usage by about 10x. And I'll show you examples of research and development that address each of these different points, just to be able to connect the dots between some of the things you're hearing from your colleagues in universities, people who might be working on the SEMIAS program or other researchers, to be able to connect the dots to some of the larger industry trends. So if we're managing to hit these different points, we're able to drive down the cost and the minimum sustainable price by over a factor of 2, providing a sustainable PV technology cost reduction to drive market adoption and potentially even enable some storage, which begins to become an important factor when you hit 20 or 30% grid penetration. So I'm going to start by talking to you about efficiency, the very first point. I won't bore you with too many technical parameters, but I want to inspire some wonder of what we're able to do in an R&D environment today, what we're able to see, how we're able to infer the problem, and how we're able to solve it. This is a Tesla motor vehicle. It's called the Porsche of Palo Alto, or the Prius of Palo Alto, because in Palo Alto, California, many of the venture capitalists are buying these electric vehicles. That's the engine that makes it drive. And in a solar cell module, you might be more familiar with these modules on the roof. Each of these different little squares right here is comprised of a wafer and a cell, and that cell is the engine of the solar cell, of the module. So if the wafer material is good, if the quality is good, then the performance will be high. And we can map the performance of a material or a solar cell by using a variety of techniques in a laboratory, including scanning laser beams of specific colors of light representing different colors of the solar spectrum, and determining how many of the photoexcited electrons in the material make it out. It's called the current collection efficiency. So if you're able to image a typical wafer like this that's transformed into a solar cell, you would see the following. Let's start over here on this. This is a full-size solar cell, and you see regions of high performance in red and low performance in blue. These numbers represent the fraction of carriers collected when you shine light on your sample. If you look at the same structure with your eyes, you don't see this in homogeneity. You just see a solar cell. That's because our eyes are not measuring current collection efficiency. They're measuring reflection of light off the solar cell. And so we see this blue-like color, which is good. Blue or dark black means that the solar cell is absorbing light. If it looked white, it means it's reflecting all the light and it's not converting any of the incoming light into electricity. So black is good, it's absorbing. These little regions of underperformance that are seen right here, if we zoom into the structure, and again, this is what Sergio spends his time doing, if you zoom into the structure, you see a variety of little structural defects that form inside the material. These are called dislocations. Here's an example of one little dislocation pit. And then around those dislocations, we have metals forming. And the scale bar right here is 100 nanometers. Does anybody have a sense of what a nanometer is? A nanometer is the distance that your beard grows between when you pick up your razor blade and apply it to your face. During that short amount of time, your beard just grew a nanometer. So this is a really, really small, so 50 nanometers, the beam size that we were using to scan the material, is 1/1000th the thickness of your hair. Right, this is really amazing stuff that we're able to do this and apply these tools. In this case, it was a synchrotron tool to study the material and to go over millimeters, micrometers, nanometers, and understand the constitution of matter. Scientists are able to do this nowadays. It's really cool. I am so glad that I was born now and not 1,000 years ago when I was beating other people over the head with a club. This is exciting stuff. But the bottom line is that we're able to determine the root cause of underperformance of a lot of these materials and trace it to trace concentrations of contaminants. Trace concentrations of contaminants. Now you know that arsenic is bad for you. You might not have stopped to think about what the concentration of arsenic that's bad for you is. You're drinking water out of a bottle right over there. If that bottle contained 20 to 50 parts per billion of arsenic, parts per billion. 1 part per billion is like 7 people on the planet, right? Part per billion is a really small number. If that contained 50 parts per billion of arsenic, it would be outlawed, right? It would have too high arsenic concentration. And likewise, if these solar cells contain parts per billion of metals, it impacts performance. So this is an example of how trace concentrations of impurities are impacting the larger system. To really study them, we need not only the tools to study them that I showed you, but also the simulation. We need to understand as we heat up our wafer and process it, how do these defects evolve during processing? And how can we improve solar cell processing using computers that are a lot faster than just going to the lab, running experiment after experiment, taking a long time, spending a lot of money, and finally getting at a local maximum instead of using computer simulation and getting to a global maximum. So we're at the point now where we're able to model or simulate manufacturing processes, how materials evolve. It's almost as if, for those who cook, you were able to take the raw ingredients, study them, input them into a computer simulation, and the computer simulation told you with a high degree of accuracy exactly how you should cook them in the oven to get the desired dish on the other side. It's a very similar thing here, except that we're saying, okay, now make it 2 times faster. I want to reduce my capital costs for the equipment. Make it 2 times faster, make it 20% better. Right? Next. Next. Oh, so we're partnering with companies to do that. Next. We're applying machine learning tools and eventually transitioning these sorts of technologies into industry. So this is one company that we worked with, one industrial partner that we worked with. You'll see the name, I think I Go ahead, next. I think I had to hide, they had to hide the name of this particular industrial partner, but nobody likes to say their material is defective, right? No industrial partner likes to go out there and say, my material is defective. So in this particular case, the baseline process was blue. This is a function of an ingot height. As they were solidifying the silicon from the bottom to the top, they would extract material from various heights of the silicon ingot, little wafers, and this was the quality that they were getting out of it, the minority care lifetime. And the red is what happened after we optimized their process, and you can see twofold improvement to the lifetime in a lot of these cases. At the bottom of the ingot, we were able to recover material that was otherwise thrown away. So this represents not only an improvement of performance, but also a yield improvement, manufacturing yield improvement. So this started out as a Department of Energy sponsored research project to study the constitution of matter, to understand how the solar cells were constructed, what the impurity concentrations were, how they were distributed. Then it became a modeling project to understand how these impurities evolved during processing, and eventually an industrial transfer project. So how that worked in my laboratory, the Department of Energy, US Department of Energy, contributed about $1.5 million. 300,000 went to an industrial partner in the collaboration, 1.2 to our laboratory. That was spent out over 3 years to develop the core technologies. And then when we worked with industrial partners, additional industrial partners, they typically chipped in about $150,000 each to tailor these tools to help improve their manufacturing processes. While the researchers, the PhD students and postdocs were working on developing the fundamental tools that were publishable, a lot of the industry transfer happened with professional staff in our lab whose sole mission is technology transfer. So our laboratory is set up to do both basic research, but also to transition this technology all the way to industry. Next slide. I have to keep going because of, okay, so to enhance efficiency, efficiency is the strongest driver of PV cost reduction. The R&D challenge is that we need tools to understand what limits performance, especially with novel materials. We need to develop the computer simulations to understand how we should process these materials, and then we need to translate these learnings to industrial partners. And this is the flow of R&D in my specific laboratory. I don't think we're unique. There are a few other laboratories doing it this way in the United States. Many of them do specialize in basic research, a few in applied research. We try to span the entire range because in interacting with industry, we get that feedback of where the industry is headed, what their new technology, where their new technology is going, and that helps inform where our basic research should be. Because in 2 to 5 years, when my students graduate, I have to position them to be useful in industry, not to have solved yesterday's problem. So in terms of some basic research, feeding the pipeline, trying to preempt where industry is going to go, these are topics that you might hear about through some of your researchers here in Mexico. Certainly, these are very hot topics in the United States as well. And my particular flavor or twist to going to very high efficiencies is to leverage existing technologies. Now, current PV technologies are in the range of 15 to 25% efficiency. The theoretical limit should be somewhere around 90%. There's a big gap in between and a lot of room for exploration, more on the fundamental side. This is far from being industrial, but it's looking and eyeing an industrial application. And so leveraging existing technologies helps the on-ramp, right? I'm thinking, where are these technologies going to be implemented in manufacturing? So one of the directions to go is to combine a silicon cell with another solar cell that absorbs different colors of light more efficiently. And so think about this as a partnership between two materials, one absorbing one portion of the solar spectrum efficiently, the other material absorbing the other portion, and together they should be able to get up to in the range of 35 to 40% efficiency. And so we've begun developing some initial prototypes at around 17 using manufacturable processes. The silicon, which we already heard about, new materials with our collaborators at Stanford called perovskite materials. These can be deposited near room temperature. And so you often hear, like in Cuernavaca, the research center focusing on low temperature processes, quick deposition methods. This is, and in fact, there's some perovskite research going on there as well. This is the class of materials that we're considering here. Low capital equipment investment. We're also considering integrated storage. There are a number of directions this can go. Maybe if we get solar cells cheap enough and batteries cheap enough, we just put Lego pieces together and combine it into systems. But if we don't get the battery technology cheap enough, and if we want higher energy density, we have to store the used electricity in terms of fuel. Fuel has a much higher energy density than electric storage in batteries. And so this is an example of a solar cell within a little bucket of water, pH neutral conditions, and a light shining on the solar cell generating little bubbles. This is collaborative work with Daniel Nocera, who's a catalyst specialist at Harvard, developing solar-to-fuel devices. Right, so if we keep going forward, one more. This is 10% solar-to-fuel efficiency that was achieved by coupling the solar cell to the catalyst part. It's thinking about this from a systems perspective, not only focusing on making a better catalyst, not only focusing on making a better solar cell, but modeling the combined system to enhance performance of the collective. And in the beginning, when we first started putting these pieces together, we were getting bubbles, but it was only converting about 1% of the incoming light into electricity. And here, using a system modeling approach, which is more on the electrical engineering side of things, we're able to get to 10% solar-to-fuel efficiency. You can see we turn the light on and off, on and off, on and off. And this device is creating fuel that we can store. So this is one example of some of the emerging directions. When we think about solar-to-fuels, we're trying to preempt the problem when we hit 20 or 30% of grid integration, and we can no longer just use the grid as our storage device. We have to have our own storage devices that can store the electricity for later. So we need, for better catalysts and for better top cell materials for these tandem structures, we need to be accelerating new materials discovery. So this is an ongoing effort within material science. We're discovering new materials all the time to make better lights, to make better protection on vehicles, make better airplanes, right? And it's not different in solar. So next slide. This is an example of a few new materials that we're developing in the laboratory. Prior to 2007, before we got into it, a lot of investment. Finally, we started seeing improvements of performance in these materials, collaborating with a group at Harvard, Roy Gordon. And the way we were doing it was measuring one little device at a time. And it was a miracle we were able to move this far along. Next slide. What we're doing now, as of last month, is making or installing intelligent experimental systems that are able to measure devices and materials in order of magnitude faster. So these are little probe tips coming down into 1, 2, 3, 4, 5, 6 devices at a time and measuring all of them, acquiring that information and putting it onto a database. The way this looks in the laboratory is you have your little devices right over here that sample, and then it's moving between different pieces of equipment being measured so you can get a full perspective, a full 360 on the device of what's going wrong, what's going right, and how to inform the next generation of devices. We might make a gradient of compositions over this little material here and explore a whole library of materials in one shot. So this is where materials discovery is headed. It's a combination of broad and deep at the same exact time. And we need this rapid innovation because this is a traditional device efficiency improvement curve, the red over here, from 1974 to current times. It takes a long time and a lot of effort if you're just measuring one device at a time. If you implement this sort of what we call informatics approach, this is a company in San Francisco that invested in this copper indium gallium diselenide-based solar cell, you could achieve very similar types of performance improvements in a much shorter time and much fewer people. So this is the impact of materials discovery and high throughput computation and characterization to assist that. Next slide. You need to library your results, right? Because now you're generating gigabytes of data and in text files. And it has to be organized and assembled in some way. So creating these libraries that not only orchestrate the workflow so that different people can communicate and collaborate, but also store the information, allow you to visualize it very quickly is important as well. And this is what we call big data, right? Applying big data, the same tools that are being used to help traffic flow in Mexico City, or to make sense of cloud cover, the effect of cloud cover on solar plants around Mexico. The same types of tools are being applied here in the laboratory to enable discovery. Next slide. I'm going to skip through the CapEx discussion for a purpose of time, if I can zoom out real quick here. But this is a fascinating discussion in and of itself. And just say, going to an era of convergence. This is a perspective I want to leave you with as we conclude our discussion today. We are in an era of convergence between traditional energy sources and these novel energy sources. PV is becoming global in terms of manufacturing and installation. Big, it's becoming a bigger and bigger factor. And integrated, it's no longer just an isolated rooftop thing. It's becoming integrated with everything that we do. Here's an example within, from 2010 to a projected 2015, and I think this is even a little bit conservative, of the demand installations, meaning where PV is installed as a function of location in the world. Europe, and mostly Germany, accounted for 4/5 of all installations, dark, cloudy Germany, 4/5 of all installations of PV in 2010. In 2015, there's a much more equitable, democratic distribution of PV installations worldwide. Why? Because that price is coming down, right? More market opportunities are opening up, and you're seeing a much broader installation. And the reason I think this graph is wrong is because I think that Mexico is going to be a big contributor to this. We had the discussion last night. Maybe not by 2015, but by 2020, absolutely. And the rest of that world, that orange part is going to open up, which further exacerbates this trend of democratization of installation. Second point, in 2012, right at the height of Chinese manufacturing, when a lot of companies in the United States and Germany were going out of business, we calculated the minimum sustainable price for PV manufacturing in the United States and in China and figured out what cost categories were really an advantage for China. And scale and supply chain, in other words, that initial capital investment, really tipped the scales. The availability of capital, dictated by the industrial policy, was pushing an advantage to China. And as the technology improved, we were predicting that this type of effect would evolve, a much more, equal or parity of manufacturing costs worldwide. Why? The simple answer is that with technological innovation, you're squeezing out some of the key advantage areas of China. You're making it, the absolute CapEx investment lower, for instance, right? So the effect of industrial policy will be less. You're squeezing out some of the materials as well by making things thinner and lighter, and that's taking out some of the additional advantage. And what we see as we go from the previous slide to this one is that module manufacturing is the first to reach parity, followed by cell, followed by wafer. So essentially you're working your way up the supply chain toward the feedstock. And you're seeing this already in Mexico. Up in the north of the country, there are module manufacturers that are importing cells from Asia and assembling the modules in the north of Mexico and then selling them to the North American market. So this trend, the convergence of supply, not only the installation but also the manufacturing, is going to be happening within Mexico. And so you'll need technicians, you'll need engineers, you'll need people who are thinking about how do we make this stuff? How do we make it well? How do we make it high quality so we don't have quality issues down the road, recalls, costly experiments that go wrong? Next slide. Next slide. Another fascinating chart. This here shows new global installations of electricity, of energy in this case. In blue, this is new energy installations worldwide in terawatts-av. And the red is new PV installations. So in the mid-1980s, when Ronald Reagan took off the solar panels from the rooftop of the White House, PV was a small, small fraction. Notice this is log scale on the left-hand side. Tiny, tiny fraction of all global electricity installed annually, new electricity installed annually. Now, in the last year, in the United States alone, solar accounted for 20% of all new grid electricity installed, all new capacity. Not capacity factor averaged, just raw. So this is indicating to you that if this keeps up for another 20 or 30 years, solar could account for 20% of all grid capacity. That's pretty impressive. And it continues to grow. So this was, when I was saying at the very beginning, a change is coming. This is really the chart that I'm referring to. I don't think it would be wise to ignore solar anymore. Solar is no longer a niche technology. It's really becoming something much bigger. And you need to think outside the module. I've told you about some of the innovation affecting module performance. It's a lot more than that. So this is module manufacturers, balance of systems, installers, electronics, equipment vendors, specialty materials. Solar cells today use 10% of the world's silver. That obviously can't keep up for much longer. We need to innovate our way out of that supply constraint. R&D, finance. Somebody has to pay for the $2 billion polysilicon factory. Somebody has to pay for the hundreds of millions of dollar field installation. Smart and, say, honest financial tools that will enable facile investment is certainly warranted. Storage and grid, thinking about how all of this ties in further downstream. These are all areas where innovation is needed, and the holistic picture of solar is also warranted. So I'm going to just share a couple of thoughts. These were thoughts that were gleaned from discussions over the last few days. preparing Mexico for the coming solar revolution. One of the interesting trends, this is 2012, second half, 2013 first half, 2013 second half. This bar right here is representing the photovoltaic levelized cost of electricity, and these are different electricity rates. The general trend is that there's an area of convergence, right? You're converging between the price of photovoltaics and the price of grid electricity. So we have this factor of 2x perhaps right now, somewhere between 100% or a factor of 2 to 1.4, somewhere in that range, where PV is just a little bit too expensive right now. But the better way to think about this are two Gaussian curves converging, right? And so they're coming together, right? One is the grid electricity prices, the other one is PV, and they're both treading in opposite directions. At the edge of the Gaussian is an exponential, and as you begin hitting that point, you have exponential growth. So preparing for that exponential growth, managing success is one of the key messages here. I think to predict penetration like a private investor, you need to think like a private investor, calculate the rate of return on investment in different regions of Mexico, given the availability of sunlight, given the grid prices locally, and to begin to preempt what might be the interconnection needs in those regions. Being able to preempt what might be the demand by investors, because it will pick up like an exponential. From one quarter to the next, suddenly you'll just be overwhelmed. It'll be like bulls trying to run out of a pen in the farm, right? A stampede. And so preparing for those moments, being able to predict when they will happen, requires being able to think like an investor. Lastly, human capital is needed. And here's where semillas, I think, can play a big role, and here's where the universities and centers here in Mexico can play a big role, and international collaborations as well. In the United States, total PV installed exceeded 10 gigawatts in 2013. It's just a big number. In Mexico, in 2014, it was about 0.08 gigawatts, about 80 megawatts. So the 10 gigawatts in the United States, 142,968 people were employed in solar in 2013. That's the Solar Foundation's National Solar Job Census. Okay, these guys are promoting solar, so you can get that number from a few different sources, but it's always in the range of 100,000 people. And all US states are benefiting, because solar is being installed everywhere in the United States. At the very least, they have the installation side. Nobody's going to come and take away those jobs. They'll be local. And at the most, you'll have elements of the supply chain that I showed you earlier, the materials, the equipment, the finance. Some element of the supply chain covers about 39 states of the US. And so there's a wide benefit to this enterprise that's growing exponentially with time when most other things in the GDP are just stagnant. In Mexico, there is 0.08 gigawatts installed in 2014 compared to over 10. So we have about 2-3 orders of magnitude to go. And you're poised for massive growth. This is really the key point. You're right at the beginning of the S-curve of technology adoption. It's going to be picking up exponentially. How are you going to prepare to have an equivalent number of people, 100,000 people, educated, ready to contribute to this workforce? Installing panels, using the best standards that are available in Mexico, developing those standards, producing the modules, doing R&D to improve the modules, translating the technology from Germany or the United States or Japan or China into the Mexican context for the Mexican weather and environment. How are you going to be preparing for all of this? I think human capital or investment in human capital is needed because, like pig farming or like polysilicon manufacturing, we don't raise students overnight. They take some investment, they take some time. So it's with that thought that I wanted to leave you an optimistic message that this is a very unique place and time. You're poised for massive growth. There will be this change coming. And the distinct challenges and opportunities that are presenting themselves, some are common worldwide, some you can learn from colleagues around the world, and others are unique to Mexico. Take full advantage of this opportunity, and more than anything else, people like me and others are rooting for your success, are hoping that it goes really, really well, and it has to for a number of reasons, and we can be your friends, we can be your colleagues in this endeavor. So thank you so much, and thanks for your interest in solar.
Muchas gracias, Profesor. If it's okay with you, we can do a short round of Q&A.
Absolutely.
So, Juan José, si alguien tiene una pregunta.
Okay, gracias.
Many thanks, Professor, for the presentation. I found it very enriching to have the academic and the policy perspective combined. And actually I have several questions, but I would like to focus just on two of them, which we've heard in the literature. We've read a lot about many coming materials for solar PV and very promising technologies for this. What is the perspective from your group? Which technology currently and for the future balances the sustainability aspects of solar PV technology? And what I mean by this is specifically for some indicators, like I'm aware that there is no ideal technology,
right?
But which one has the best trade-off between levelized costs, between human toxicity potential, among the resource availability, and especially because we hear that the International Energy Agency is making a big assumption there with solar, solar thermal, solar PV. Germany is doing the same, and China as well. So that would be my first question.
Sure.
And as well, looking at this from a life cycle perspective.
Maybe I'll address that right now. The ideal technology is one that is high efficiency, low capex, low materials use, is scalable, and is reliable. Right now, silicon has 3 out of those 5, and many thin film technologies have 2 out of the 5, and they're perfectly symmetric. So silicon is high efficiency, it's reliable, or bankable, that's a better word for it, bankable, meaning you can acquire investment for it. And, but silicon is not manufacturable necessarily, it has high capex, it's a large barrier to investment, and so I think if you look at this global perspective, you can see certain advantages thin film, certain advantages silicon, and they're both converging to the same cost structure. So thin films are improving their efficiencies, and silicon is trying to streamline the manufacturing process. Thin films are trying to improve their reliability, right? And so you see this convergence, and it's very, very fascinating to watch. In the past, 20 years ago, thin films and crystalline silicon were like 2 different worlds, and now they're converging. The device architectures even are converging. I can geek you out with talks of carrier selective contacts, but some of the highest efficiency silicon and highest efficiency thin film device architectures look very alike. So I call it an era of convergence right now. From a policy perspective, I think it's a little precautious to pick winners. I don't know which side of the mountain will be climbed faster. But I think it's important to identify the major challenges and to galvanize groups of researchers around those challenges, right? To make them aware that, okay, the reason I'm doing this basic research is that we'll connect up to solving this challenge. So just to picture what a capex reduction would do for a silicon cost structure, let me pull up one quick chart. Won't bore you with the details, but this is one slide, right? So this is one slide showing you the factory of today. 10x lower capex, factory of tomorrow. So the cost went down from 2 billion to 200 million. And here, 100x lower capex, the cost went down to 20 million, which you can raise from virtually any bank, right? $2 billion, there's only a few large investment banks that can do that sort of investment. And meanwhile, the minimum sustainable price drops by 46% over this range. So if you could go from the capex structure today to something much more streamlined, even a 10x reduction of capex, your cost structure looks almost like a low-temperature, solution-processed perovskite cost structure would. And so that's when I'm mentioning that they're climbing the same mountain from different directions. It's capital equipment, it's efficiency, materials use, bankability or reliability, and scalability. To address your scalability concerns, there's a couple of other indicators that you'll want to consider. One is energy use. To refine silicon at 5 terawatt factory levels, so 5 terawatt peak is almost a 10-20% electricity production rate, you would need about half of all the electricity produced in the United States today to power that factory. So we need to decrease the energy intensity of our feedstock refining. Another interesting tidbit, that factory would be the size of the state of Rhode Island, about 2,000 square kilometers. So we need to streamline the manufacturing process simply from a land use point of view. So you can identify these key technological challenges and then orient the R&D to address them. But as I look at it, thin films, climbing one side of the mountain, crystalline silicon the other, both have their challenges.
So perhaps to have a set of indicators.
Yes.
Select a data, and then do a multi-criteria decision analysis.
Sure.
Rank those technologies and to see from which perspective they might.
You could do that. If basic R&D were predictable and you were able to estimate the rate of improvement to a high degree of confidence, that would work out really, really well. You'll do that analysis, and if you include reasonable uncertainties in R&D, your error bar will probably be larger than the bar on the chart itself. Right? Because discoveries happen, right? Somebody might come up with something that completely changes the world. A new material might be discovered, and within 2 years, it's accounting for 5%, and the next year, 30% of all global electricity production. So it's hard to predict sometimes. But I encourage you to do the analysis, because at the very least, you'll identify the parameters that matter most. You'll be able to chart where we're at today, do a sensitivity analysis around that point, do a Pareto chart, a tornado plot, and understand what are the main drivers, and then try to communicate them or connect them to some of the R&D that's being done, as well as the industrial R&D.
Les agradezco, antes de hacer la pregunta, presentarse para nada más saber un poquito quiénes son.
Sí, gracias.
Hi, thank you again for the conference. I'm Alejandra Espinosa. I'm just entering the ministry. I'm in the hydrocarbons division.
Okay.
My question is more towards, you were talking in the beginning about command and control policy in Asia and how this drove the development of PV. And then thinking about MIT and Cambridge being such an important hub for development and industry interaction.
Yep.
I was wondering, in your opinion, and seeing the moment where we're at in Mexico, trying to develop national content, and not only for renewables, but for all the energy industry, what will your recommendations be to enhance the collaboration between academy and industry to make sure that intellectual property is protected, but that inventions are marketable, that they do it at a fast pace, and just understanding where we're at now.
Okay. If you have an hour or 2 hours after, I'd be happy to go have a coffee with you. Short answer. So human capital development is a very important part of it, especially in a fast-growing industry. The second important part is creating the forums or the fora for discussion and collaboration. A lot of our understanding of where to position ourselves as a research laboratory, where to have the biggest impact, and to feed the pipeline of innovation came from our industry interactions. So it takes a lot of effort. People are constantly turning over in industry. The faces change. It's a relationship management issue. You need to manage the intellectual property and the confidential materials, and students' minds aren't wired necessarily to protect that sort of stuff. They talk freely about everything, so you have to partition, stonewall information. But all that can be managed. What is priceless is getting an industrial partner with whom you've had discussions for the last 18, 24, 36 months to finally start opening up about things to you. During a factory visit or a tour or some discussion at a conference where they say, listen, I'm not supposed to tell you this, but this will really help solve this problem that you're working on to help us right now. Boom, right? Don't share it with anybody. And suddenly you're like, oh, I get it. You wouldn't have ever had that perspective. That seeds the next generation of R&D ideas in your lab, the fundamental research. It helps solve a near-term problem that they're dealing with right now, and you're translating the technology to the factory. And that type of informal interaction, building that trust, is, I think, a very important element of it. So establishing the right fora with the right incentives is important. And then I think a large part that you can play a role in here is just bringing pieces together. I see some people in the back from Green Momentum and others who are pieces of the ecosystem here, right? And I think every PV researcher wants to see their technology go out into the field. That's their dream. The reason we're here and not working in a big bank on Wall Street is because we want to see these technologies go into market. We want to see our inventions go into the field. And at Cuernavaca, there are examples in the research center of thin films on windows, reflecting some of the infrared light and cooling the rooms inside, and on some of the awnings and public outside. And I saw them applying their technologies locally, right, to their building, to their local environment. And that sort of entrepreneurship, if given the right resource and given the right incentives, will really go far. Yesterday during the talk at UNAM, there were two groups of people who came up to me afterward. One gentleman who started his own company as a consultant to help facilitate grid installations. I mentioned there were 50 megawatts of solar on the grid here in Mexico. He helped facilitate 0.5 of them. And he came up to me, not a hair of gray on his head, just a young guy straight out of school doing this for a living. Another 2 ladies came up to me, good friends from school. They started to form their own installer company. They installed 5 systems so far throughout Mexico, and they were asking me basic questions like, how do I source wafers? Is there an industry association for our type of installer that can work out together some of the pre-competitive issues and maybe make recommendations for policy? Can we connect these young entrepreneurs with people like the folks at Green Momentum to help give them a chance, to give them hope that things can move forward? Can we, like Sergio is where? Right here in the front, right next to you. Sergio is a PhD student at MIT. How do we open up the young students' eyes that there are pipelines, opportunities available for them? How do we open up the idea that all this expensive equipment that has been installed in all these research centers throughout Mexico, maybe those people who use the equipment can come over to MIT or Harvard or other places and be trained on how to use them to greater effect to increase the productivity of those tools? It's the human resources training. It's stimulating the young minds who have their careers ahead of them, who are willing to take that risk, don't have kids yet, and are willing to go out and take that risk and form the companies and try to facilitate this coming energy revolution in Mexico. How do you create the conditions and bring together the different stakeholders in this transformation and enable them, empower them? So that's where I think some of the bigger impact can be. Human resource development, empowerment, recognizing the available pieces that you have today and starting to bring them together in an ecosystem. And something as simple as having a monthly social here within the ministry. You have a great foyer area. If you pay for tequilas and wine and cheese and invite the major players here within the entrepreneurs sector and the solar sector and some people from the ministry just to get together once a month, invite them up from Cuernavaca, hour drive, no problem. And people mill, people talk, and suddenly connections start getting made. Right? So this is the type of connection that I think is really stimulating and important. And that's what we did in the Cambridge area that led to a variety of new activities in our area. I used to pay out of my own pocket the pizzas for these solar socials.
Well, hi, my name is Ingeniería. I also just started working here. Congrats. And I have a question, and it's not about the presentation, it's more about the measures, the policy making that they are adopting in European countries such as Germany, United Kingdom, Spain, in order to strengthen and to develop renewable energy. I don't know if you know about this subject, and if you know, what is your opinion and what will be the recommendations that you will give in order to promote the use of alternative energy? Because as you say, the costs are it's not as cheap as we think. It's actually really expensive, right?
Right. So I'm going to pick a couple of good example and bad example here. Maybe cherry picking specific policy elements that I think worked well or didn't work well. So Spain was a very interesting case. They, let's see, in the mid-2000s ran their big experiment. So for a couple of years there, they were accounting for a large fraction, tens of percents of all global PV installed, and then they crashed back down to zero. So what happened there? Years before that, they implemented a feed-in tariff, and it wasn't generous enough. They did it right before Germany turned on theirs. And so the installer, or the manufacturers of modules and the installers decided Germany is a more lucrative market for us. We're going to be doing our installation of modules there. And modules are a fungible commodity. They're a commodity. They're a global commodity. And so they'll go to wherever the price is highest. And they went to Germany. So the Spaniards took a step back and said, well, wait a second. We didn't set the price high enough. Then they set the price pretty high, right as Germany was ramping down their tariff. And suddenly the rate of return on a Spanish installation just went through the roof. And so modules sloshed over from Germany into Spain. And you had this scramble for installation companies to, overnight having to grow, having to train people, having to do the installations. Years later, there were some reliability issues because of that too fast growth. And I think some of that could have been avoided if there was a little bit of thinking like an investor. On one of the previous slides here, I showed calculating the rate of return. I mean, as you're democratizing the energy sector, opening it up to private investment, you will be dealing with people, private investors, who are thinking like a private investor. They're calculating the rate of return on their investment in a solar power plant in Mexico. So you have access through CMEs, through other sources. You know what the insolation data is. That's the amount of solar resource in each of the places of the country. You know what the utility rates are. You know what some of the interconnection issues are, the local taxes. You could calculate the rate of return with a high degree of granularity and predict what the investor is going to be thinking. Then you know more or less what level they're at, what the rate of return is, what the hurdle rate might be for them to actually invest, and you can predict based on your conversations with other technologists and other people in industry what the prices are going to do in terms of modules in the future. So that's step number one, learning from the Spanish experience. A couple years later, it collapsed. There was the financial crisis. Spain was losing a lot of money because of the real estate issue, and they not only killed their incentives, they went to zero, but they also started implementing retroactive changes, which just killed trust. And so all of these installation companies that overnight ramped up, gained expertise, suddenly they were in a very adverse business condition, and many of them went under. Germany implemented a phased declining tariff versus time, right? So they calculated the rate of return, figured out what investors needed, and set a declining tariff over time that was reevaluated as needed over time. And the interesting thing, if you look at the tariff rate and you look at the price of module installation, the two track, which means it was a value-based pricing environment. The installers knew exactly how much they could ask for their installations, and they charged that much. And so it was one of these uncomfortable dances between the German government and the installers, right? Where they were trying not to step on each other's toes. And each tugging, the installers wanted a higher tariff, the German government wanted to pull it down, and they've been scaling it down over time. And Germany has, what, 35 gigs installed? It's huge. They're by far, I mean, US is just over 10. Germany is way up there. So that, I think, is better. In the United States, how to do things right and how things aren't being done right. And a lot of it boils down to a compromise between what would be ideal and what the political pressures are. Right? So it's that compromise between the two. And the best you can do in the ministry, in my personal idea, is to think like an investor, is to develop those cost models to understand what your investors are going to be wanting and what they're going to be doing, and try to predict how that S-curve is going to look like. So you can develop the policies that help prevent bad things. Well, the US Department of Energy has a really good cost analysis group. And so I have great, deep respect for the US Department of Energy. They work with the National Renewable Energy Laboratory, a sponsored lab. So EERE, the Energy Efficiency Renewable Energy Group, in particular Lydia Sekaric, who does the Tech Transfer Group, Libby Wayman, who works with technology scaling. They're in constant communication with the folks at NREL, Mike Woodhouse and others, doing the cost modeling. They have their own Washington unit with Bob Margolis and Daniel Feldman. And they produce quarterly updates of the market analysis. It's an internal document, PowerPoint presentation, but they're very well informed of what their market is doing in the United States and globally, both in the supply and demand. So that's a good example. Unfortunately, the United States, quite frankly, we only have 2 out of the 3 branches of government sort of working right now. And so it's hard to get things passed through the legislature. And translating those excellent insights into intelligent policy is more challenging in the US than I think it is here. Yeah. Thanks.
Alberto, I work for a sustainable web company. I have 2 questions. My first one is, I read something about using materials of batteries.
Yeah.
And I think it's the MIT research team.
Yep.
And if you can tell us something about that.
Yep.
Because you can recycle the batteries and use that material for,
Okay, yeah.
For the models. And my second question is if also you know something or you do some research regarding using models but in other applications, maybe not the product used for manufacturing, but for example for the roads and for other applications.
Yep, okay. So one of the questions was, I'm going to broaden the question to recycling. In this particular study, a group led by Paula Hammond and Angela Belcher were taking lead-acid batteries, recycling them, extracting the lead, and creating a new, as of yet uncommercialized material called perovskites, the one that I mentioned here, methylammonium lead iodide. So the lead within the methylammonium lead iodide came from the battery. Developing recycling technologies is important because we're going to be having, when we hit the terawatts level, this is maybe several decades out still, but we're going to be producing about 40,000 square kilometers of solar panels per year. We're going to be processing a mass, the equivalent of the Empire State Building, of raw materials into solar panels per year. And this is a massive amount of material. Right now, the market signals are not there in the United States, I'm not sure about here in Mexico, for recycling of these high-tech electronic products. Things like cell phones oftentimes wind up in the city dump. There are technologies to recycle these products, but they're not cost effective. It is cheaper to get extracted material from the ground, process it into a new product, as opposed to recycle the old ones. So I think until the market signal, either by resource constraints or because the Mexican government or the US government says, wait a second, this isn't smart, let's recycle, that sort of market signal counteracts the will of the people, which is to get the cheapest possible product. We're going to continue to see new materials converted into solar cells and a big stockpile of waste, which is a pity. And so it's something to think about longer term. Your second part of the question was?
If there's another kind of application for models.
Yes. Yes, yes. Okay, so as the price of solar cells decreases, 1.5% of what it was 35 years ago, the application space of solar increases as well. And so some of the things that we're looking in our laboratory is powering autonomous devices. Right? So one of the big problems with solar is that it commoditized a little too quickly, right? The Chinese ramped up manufacturing and the prices dropped much faster than many predicted they would. And so it's hard to add value back into the module itself. But you definitely add value when you integrate the module with a synthesized product and then sell it, brand it to the customer and sell it. And so we're trying to consider high value applications where we combine solar with microelectronics, with communications devices, and form low energy electronic systems, or LEEs for short. And so this is the area of emphasis, the systems area that our laboratory is investing in right now.
Thanks.
Yep. Muchas preguntas.
La última pregunta, tenemos que dejar sala y otra reunión.
Okay.
Well, first of all, thanks so much for this presentation. It was fantastic.
Okay.
Also, overall, thanks so much for accepting our invitation to come to Mexico. I think we benefit greatly from having you here, and I hope you enjoy your stay here.
Absolutely.
We hope to see you soon again, with some drinks maybe. Anyway, I think, if I were to, mention what takeaways are for me at least, are that, it's about long-term planning because of the cycling and supply. It is about focusing on new areas of research such as materials and efficiency. It is about preparing for manufacturing parity. Mm-hmm. It's all about the democratization of solar technology, trying to come up with better models.
And people. Yep.
And yeah, that was actually my question at the end. The numbers you mentioned, you had like 10 gigawatts already installed in the US, creating 150,000 jobs. That gives me like 50 jobs per megawatt. Is that something that we can actually assume as a rule? In Mexico, we're shooting for 1 gigawatt by the end of the present administration, which means that we'll be creating about 15,000 jobs. However, if we're talking about manufacturing parity, there is a chance that this number could double or triple perhaps.
Yep.
So you take on that.
Yeah, you're on this S curve right now, right? And it's very hard to predict when you have exponential growth where you're going to land. Small differences in the x-axis yield very large differences in the y. So that's one thing to keep in mind. And so when it comes to human capital, the reason I put this slide up was to be provocative intentionally, is to make you think about, gee, how are we preparing for this? If the lead time for human capital development is 2 to 5 years, right? Or worst case, best case scenario, maybe you have a targeted training program in a technical college for people doing the installations that might be a certification program that lasts 2 months or 3 months, right? So you have a time constant involved there, and you're hitting this exponential growth. How do you prepare? How do you plan for it? We picked out the US numbers because I interact a lot with people in the US, both policymakers, industry partners, and so I know the numbers, or Sergio and I know the numbers together a little better. But for Germany, Japan, China's a weird case. We'll leave that out for now. It's another discussion entirely. Their capacity adds are more reflective of a demand pull, absorbing the excess production from some of the favorite companies rather than necessarily a market-driven technology adoption. But if you look at the market-driven countries, US, Japan, Germany, and try to correlate the amount installed to the number of jobs, you'll find the same order of magnitude. Right? So Germany has 35 gigs installed, and the number of jobs is similar, right, to these numbers, a little higher. So I think your estimate, 50 per megawatt, is about right. And there are some more detailed studies that break this down into different types of jobs. And I think we'd be happy, Sergio has some of those numbers and that information, be happy to share it with you. But this is intended to be provocative and to make a little further what the human resource needs will be. Okay, well, thank you. Yeah. Thanks for your hospitality and your interest. Yep. Good luck.
Bueno, nada más para cerrar, agradecer muchísimo a todas las personas que trabajaron muy duro para organizar
Good.
esta visita.
Okay.
Nada,
Yeah.
Prefer Pedro, Hernán, Luis,
Hold on, let me turn this off.
Sergio,